Imagine drawing a line on a piece of paper. This line represents one dimension. Now, draw another line perpendicular to the first, forming a square. The square exists in two dimensions. If we add another dimension extending the square upwards, we get a cube. This cube occupies three dimensions, the familiar world we experience daily. But what about a fourth dimension? This is where things get tricky for our three-dimensional minds. A tesseract is a four-dimensional equivalent of a cube. Just like a cube is made of squares, a tesseract is made of cubes. Visualizing a tesseract directly is difficult, but we can use analogies and mathematical models to understand its properties. Interference geometry theory, or TGI, proposes a novel way of looking at the universe. It suggests that the fundamental building blocks of reality are not just particles, but geometric structures existing in multiple dimensions. These structures, influenced by angles and relationships within higher dimensions, give rise to the particles and forces we observe. Think of it like this. Imagine a guitar string vibrating. The different ways it vibrates produce different musical notes. Similarly, TGI suggests that different vibrations or configurations in higher dimensions correspond to different particles. The theory attempts to map these configurations using a language of angles and dimensions. TGI suggests that each fundamental particle, like an electron or a quark, corresponds to a specific set of angles and dimensions within this higher dimensional space. These angles and dimensions dictate the particle's properties, such as its mass, charge, and spin. Imagine each particle as a unique chord played on the fabric of space-time. The specific combination of notes or dimensions determines the particle's identity and behavior. While this is a simplified analogy, it helps to grasp the core concept of TGI, that geometry, not just particles themselves, plays a fundamental role in shaping the universe. To further illustrate TGI, let's consider some everyday analogies. Imagine a projector shining light through a cutout of a shape. The shadow projected on the wall represents a lower dimensional representation of the original object. Similarly, TGI proposes that the particles we observe in our three-dimensional world are like shadows of higher dimensional structures. These structures exist in a realm beyond our direct perception, but their influence manifests as the particles and forces we interact with. One of the biggest challenges in modern physics is unifying quantum mechanics, which governs the microscopic world of particles, with general relativity, which describes gravity and the large-scale structure of the universe. TGI offers a potential bridge between these two seemingly disparate theories. By suggesting that both particles and space-time itself emerge from a deeper level of geometric structures, TGI hints at a common framework for understanding both the quantum realm and the cosmos. Section 6. Unifying forces through geometric principles. TGI doesn't stop at particles and spacetime. It goes further to suggest that the fundamental forces of nature, such as electromagnetism and the strong and weak nuclear forces, also arise from these underlying geometric principles. Imagine the different forces as different types of interactions between these higher dimensional structures. Just as different shapes can fit together in various ways, different configurations of these structures could give rise to the different forces we observe. Section 7. The role of string topologies in TGI. TGI also incorporates the concept of string topologies. These are not the same as the strings in string theory, but rather refer to specific configurations and relationships within the higher dimensional geometry. These topologies, like blueprints, dictate how the dimensions interact and influence each other. Think of these topologies as the rules of the game that govern how the particles and forces behave. They determine the allowed configurations and interactions, shaping the overall structure and evolution of the universe. Section 8. Potential implications and future directions. While TGI is still a developing theory, it holds profound implications for our understanding of the universe. If correct, it could revolutionize our understanding of the nature of reality, shifting our perspective from a particle-based universe to a geometry-based one. The unification of physics, providing a framework to connect quantum mechanics and general relativity. The origin of the universe, offering new insights into the Big Bang and the fundamental laws governing the cosmos. To further develop TGI, researchers are exploring its mathematical framework and seeking experimental evidence to support its predictions. This includes developing mathematical models to describe the proposed higher dimensional structures and their interactions, making testable predictions, identifying specific phenomena that could confirm or refute the theory, exploring connections to other theories, investigating potential links with string theory, loop quantum gravity, and other approaches to unifying physics. Section 9. Conclusion: a new perspective on the universe. Interference geometry theory offers a captivating new perspective on the universe. By proposing that geometry lies at the heart of reality, it challenges our conventional understanding of particles, forces, and even space-time itself. While still in its early stages, TGI has the potential to revolutionize our view of the cosmos and pave the way for a more unified and elegant understanding of the laws governing our universe.